Okay, fine. So thank you. Long introduction. Göran Selander from Ericsson Research, and I've been working with IoT-related research for 7 or 8 years. And we started off working with specific verticals, specific industries like smart grid, mobile health, and even smart home applications. And we realized after a while that there is a great deal of overlap between security requirements coming from different industries. And with that in mind, and there is also the business aspect that if you are deploying one solution, you would like to reuse it in other industries when you develop products and services for other industries. So with that in mind, we started some work on protocols that are usable across multiple industries. So we also noticed that there is a lack of security protocols that was targeting the very constrained devices. So the presentation I'm giving is sort of following up very much on what Martin presented on certificates and enrollment, and what Shahid presented here. And I'm specifically going to look at these application layer security protocols, which we have developed to target, first of all, the generic problem of confidentiality, integrity protection, authentication, authorization for very constrained devices. And secondly, to see how these can be standardized. So standardization, as many of you know, is not always a straight path. And in fact, we've been working with standardization for 4 years now, and I mean, it's not one individual protocol, it's a protocol suite actually. And what I will come back to is sort of the importance for us to have a standardized solution, because when we are going to scale things in terms of multiple industries, we need to have solutions that are generally accepted and that are standardized. So when I was preparing this talk, I was thinking, now we are doing work which we started standardizing 4 years ago. Is this still work? How can I convince you that this work is still relevant? Because IoT is a very rapidly developing area. So I did some search through what do analysts think today are the most important technologies to develop in IoT security. So this is not a very advanced search. It's basically what you can do yourself by Googling. And you get these research institutes like Gartner and Forrester. And what you find out is that they are still emphasizing a lot of the basic security. And I will try to show examples of that here. So Gartner is listing as, generally speaking, that IoT security is the top technology for IoT at all. That should not come as a surprise to anyone here. And it also says that, quote here, the IoT security will be complicated by the fact that many things use simple processes and operating systems that may not support sophisticated security approaches. So they're actually addressing very basic security functionality. Forrester Research lists the 13 most relevant and important technologies for delivering Internet of Things security. And then they have some classification system where they have different trajectories, one which they call significant success, and they rate these in business value add. So whether it's a major or medium business value add. And that's these 2 slides here, which is a background then for the rest of the talk. So on the top of this list from Forrester, and also this is Forbes compilation of Forrester's work, is IoT network security. It's the basic setting. How do you protect the network in terms of encrypting and integrity protecting end-to-end? And this becomes more challenging than traditional networks because there's a wider range of communication protocols and device capabilities. And the second on this list, they put IoT authentication, how end users authenticate to the IoT devices so that they can control their data. On third point, you have also traditional strong security point. It's encryption of data in rest and in transit. And again, the statement is that the wide range of IoT devices limits the ability to have standard encryption process and protocols. And that's what we also saw in this our early work here is that many of the standard protocols are not really, doesn't really work for the very constrained devices. And here are the three remaining on this list. It's the topic that Martin was addressing. How do you provide X509 digital certificates and key lifecycle capabilities to these devices? And coming down now in the more medium range in terms of importance, they listed security analytics, providing actionable reporting based on policies, and API security, which is how you control the data in transfer using some typically some REST-based API. So this was the background, and I will now elaborate a little bit on these, what they call these important technologies or important properties, and then I will move over to the protocols that we are actually working on. Oh yes, there was one more quote from Forrester here. They said, they make the following observations, that IoT requires an end-to-end approach from cloud to device. Encryption is an absolute must, considering the privacy considerations. IoT scenarios places a premium on scalability because you have a large number of devices. Security analytics will play a significant role, and IoT standards are an important catalyst. So, end-to-end security is something that's mentioned in these reports. And it turns out that that's a term used in many contexts, and it may have slightly different meanings. So we have experienced at least 3 different meanings of end-to-end security that seems to be important to the people and the companies we are talking to. And one is the basic setting. It's all about a client, a server, say, having a confidential and integrity protected connection, but there may be different types of intermediary nodes which prevents this from happening. And the first one is a basic store and forward scenario, which is very common in a constrained device setting, because the end device, let's say it's a constrained server, it may be sleeping, like after having a long morning before lunch, maybe falling asleep regularly, and therefore you need to have an intermediary device which is receiving the messages, storing the messages, waiting for the device to wake up. So this is an active entity, the forwarding proxy, and you need to have, but you don't want to trust it, basically, because that would create another point of attack. So you would like to have the end-to-end setting, but still allowing certain operations by a forwarding proxy. Another type of end-to-end security is to look at what is it transporting, what kind of transport protocols are you using. Is it reliable transport? Is it unreliable transport? Maybe it isn't in the last hop even IP. Can we still provide end-to-end security? And today's protocols doesn't answer this question. The existing standard doesn't manage to do this. And the third aspect, which I learned in a discussion with the Open Connectivity Foundation, which is one of these industrial consortia, which defines a set of groups, a set of standards for deployment. And they say that, well, we are using many REST-based protocols, or in particular we are using HTTP and CoAP. And we would like to see end-to-end, starting with an HTTP client, which may be a browser or something, or a WebSockets interface, and ending with a server, which is a CoAP server. Can you also manage end-to-end across this, so that you actually change protocols, with protocol translation, but still maintain the basic semantics? So that's 3 aspects of end-to-end security. And related to end-to-end security, you also have at what layer you're doing the encryption, or the actual protection of the message. So if you look at link layer protocols, you will get a very well-protected object because you're protecting everything above link layer, but you only get it as far as the link extends. And then you will have a clear text message, and you will make another encryption for the next hop. You will hop by hop security, but a large part of the message. If you compare link layer, and then if you instead protect the message, you go higher up the stack, it means that more of the metadata will be revealed, but you will in general get longer hops of security. So if you extend all the way up to application layer and only encrypt the payload, that means that you will definitely get end-to-end from application to application, but you will not have any protection of the metadata. And it turns out that there is a sweet spot where you can allow certain metadata such that certain metadata be possible to read, but not change. So you can allow these forward proxy operations without the proxy being able to decrypt the payload or change the metadata. That's been the basic layer we've targeted, and this is the reason for the label application layer security. It's addressing the application protocols and the transfer protocols which are used with the application. And the third general remark I'd like to make about these statements from the analysts is about scalability. And it's not only scalability to a number of devices, it's scalability across different deployments, across different device types. And for this reason, we realized we need generic security enablers which are suitable for a range of devices, from unconstrained to very constrained. And this is, we've already been discussing this, what kind of CPUs and RAMs are we looking at, and we're thinking of RAMs of the order of tens of kilobytes or maybe hundreds of kilobytes, and power and relevant for processors that can live for 15 years or something like that. And for unconstrained devices, there is no problem having a very restricted processing, because that is only contributed along low security overhead. So that's actually always desirable. And it's important to stress here that we don't want to compromise on security. So even though we are looking at devices which are not very powerful, they can still do, for example, symmetric key operations which are state-of-the-art. But what we like to avoid is things like large messages, message size, number of round trips, because that leads to a lot of power consumption. And finally, we need to align with relevant IoT standards which already exist if we want to have a large deployment. And here is the suite we are working on is the IETF co-op suite. And on top of that, the device management protocol by OMA, and then the IPSO smart objects, which is adding a more elaborate object model on top of OMA lightweight. So that's, for example, that's used by IKEA through 3. So now the rest of the talk is about this actually. It's about these protocols that we have been developing, and I will give some examples and some more technical details. So they range from, there are 5 protocols or 5 names here on the left-hand side. So they range from ready standards at the top to first draft at the bottom. And if we start from the top, we have something, I will provide more slides with details later, but we have something which is called COSE, C-O-S-E, which is a secure message format designed for constrained devices. And it, in turn, is based on an encoding format called CBOR, which is, I'll show you a separate slide on, which is a very compact and efficient way of encoding data. And the other protocols, the other R protocols, they are based on CBOR and COSE. So that's basically the fundament. And they are also using CoAP, which is this RESTful protocol for transport. So just going through them quickly, we have OS CoAP, Object Secure CoAP, which is a secure communication protocol based on this encoding CBOR and secure message format COSE, and using CoAP for transport. We have ACE, which is authentication and authorization in constrained environments, which is a lightweight authorization and access control protocol, which is a version of OAuth, the web authorization protocol. We have AdHoc, which is ephemeral Diffie-Hellman over COSE, which is a key exchange protocol, what you do to generate fresh keys between 2 parties. And we have a new protocol called EALS, Enrollment over Application Layer Security, which is is looking at the problem that Martin was formulating previously about how you do a lightweight enrollment for constrained devices. So starting from the bottom again, CBOR. CBOR is concise binary object representation, and it's really cool. So you should have a look at it. If you're at all interested in encoding of data, you should have a look. It's basically how do you, in a clever way, encode data. So if you have a byte, and you want that byte to represent both an integer or a float or an array or a string, how would you do it? I mean, usually either you have a schema which tells you how it's encoded, or you have some sort of tag length value where the tag tells it what kind of data, the length of the data, and the value is the value of the data. So what it does, it takes basically this byte, this 8 bits. So you take 3 of the bits, and that's the tag and length. And then you have 5 bits for the data. That's sufficient for a certain amount of data. And if you need more for the tag and length and more for the value, then you will have an extra byte for the value. So you can see how encoding is done. I will not go through this, but just as a teaser, this creates a very compact way of coding data, and it's also very easy to parse. So this is suitable for very constrained devices. And a lot of the work that is done in the IETF, in the Internet Standardization, when it deals with IoT, it's using CBOR because it's such a very efficient way to encode data. The next step up is that we take CBOR and now we build secure messages. And the secure message typically is something like the boxes at the bottom here. It's a header with some metadata saying what algorithm am I using, what key am I using, and then basically comes the blob which contains the encrypted data. That's the one to the left. Or if it's a signature, then you have the header saying what is the signature, what public key should I use to verify this signature. Then you have the object which is signed and the actual signature data. An example on the right-hand side. Algorithm, key identifier, payload, and the large part here is obviously the signature. So if we want to reduce data carried to these constrained devices, we would like to reduce the signature, which is a hard challenge because so far we have very large, I mean there are various schemes here, but this is sort of a challenge in the crypto community. How can you make smaller signatures? So that's COSI. And now we come to the protocols we've been more closely, which is sort of 6 and Ericsson proposals to this standardization community, and that's object secure co-op. So given that we have CBOR implemented and also COSI in many of these devices in the near future, and also co-op, which will be the communication protocol, we add now a thin layer which is doing encryption of co-op messages. And it's basically taking a co-op message, the essential part, which is, you can think about the HTTP message, and you wrap it with COSI, with this secure wrapper. And then you take that format and you put it back into a co-op message and send it. So the additional overhead you will generate is of the order of 10 to 15 bytes, which is very, very small actually. And then there are some information about how this works. This protocol is designed so it actually complies with all the 3 end-to-end security scenarios that we've discussed previously. So it's both supporting forwarding proxies, it's independent on underlying layer, it works even without IP, and it can do these RESTful transformations from HTTP client to co-op server. So you actually have a complete end-to-end secure solution, which is very compact. It supports things like notifications, if you have publish, subscribe, and the fragmentation schemes, which are defined in co-op. And it is also extendable to group communications, which is something that we worked a lot together with 6 on, to look at multicast requests and unicast responses, which is, for example, in a lighting scenario, you may have multiple receivers of a switch sending out, or you may even have multiple switches. So you have a group communication scenario. And that's the type of setting where this would work. So this is a little bit more details about OS co-op. It's basically taking an existing co-op request. This is from an implementation point of view. You can think of these dotted areas as the OS co-op processing. It's taking a co-op request, it's encrypting it, and on the other side, it's decrypting it. It's using a certain COSI format. It's based on an authenticated encryption algorithm with additional data, which is state-of-the-art encryption. It's mandatory to implement a certain algorithm called AES-CCM with 128 bits key, 64 bits MAC, and an IV of 7 bytes, I think. And encrypts all part of the co-op message, which are not intended for an intermediary node. And this can then be used either instead of DTLS or as a complement to DTLS. And it's lightweight in terms of implementation. So we have people here in the room from SIX who made very nice implementations. So it's implemented in Contiki, adding of the order of 10 kilobytes. Now I'm looking at Martin. Okay, so if Contiki is of the roughly order 50 kilobytes, it adds something like 10 kilobytes. Contiki with co-op and with UDP and with all the network stack. And then we have, and then we also have very nice message overhead, which is basically what we are trimming this protocol for to lower the power consumption. So it adds something like 10 to 15 bytes of overhead, and in this set of overhead, you actually include an authentication tag of 8 bytes, which you can't get away with. That's essentially the signature of each message. So it's only a few additional bytes being added. So far, that was one of the protocols, and now I'm moving over to another protocol, which we are working on, and that's called ACE, the authentication, authorization of in-constrained environments. And here we have sort of this is the step before you want secure communication. It's the step, how do I authenticate and authorize? So you have a generic problem where the client needs to access resources of any kind, and you want to authenticate and authorize the client and server to each other. And the IT setting here is, of course, that the resource server may be constrained, even the client may be constrained. They may not have connectivity all the time, or maybe only the client has connectivity, or they may have lost time synchronization. So there are many aspects to think about which are not a problem in the internet setting. So the proposal here is that we actually use a protocol designed for the internet setting, the OAuth 2.0, and we adapt it to the special considerations, conditions of IoT. And so there's another slide on, so there is 2 parts of this work. One is the framework, which is generic, works for different kinds of deployments. And then we have something called profiles of the ACE framework, which depends on what is actually the communication protocol you're using between client and resource server, because that might be different. It might be that you're using HTTP or co-op. You may be using TLS, you may be using some other security protocol, you may even be using MQTT or some other technology. And that's taken care of by the profile, which then specifies the interaction between client and resource server. And the basic protocol looks like this. And you have a resource owner. This is the guy that owns all the sensors or actuators, which are the resource servers. And he provides the policies for those to an authorization server. This could be a web interface or an app interface. And so the authorization server is authorized to handle this resource server, and they have a pre-established relation. And now comes a client, and the client wants to access this sensor, it wants to turn on this light bulb, it wants to control this actuator. So it needs to first authenticate and authorize with the authorization server and get an access token back. This access token, it contains the information for the resource server. Who is this client? What is this client entitled to do? This access token, by the way, is a COSI object. It's one of these signed objects we talked in the beginning. Everything here is encoded with CBOR. So this is based on the same type of primitives. So the access token is then provided to the resource server, and within the access token there is also a key to the client. It could be a new key which is distributed to both the client and the resource server from the authorization server, or it could be the public key of the client. And then the resource server can authenticate the client, and it can verify when the request comes if this client is authorized. So it's a very simple protocol. It's mapped out to the web-based protocol, web authorization protocol, but it's adapted for the constraint set. So I mentioned key establishment, and that is a generic problem, obviously. How do you get the initial keys in place? Or how do you get the keys? In this case, the client and server may never have met before. This may be you're giving a key away to or you're lending a key to a carpenter to come into your house, and you want the client to have access, the client to have the key for a certain time, and the server be aware that this is a new client that should have access to this key. So the server is the lock and the client is the key in this case. And so there are, one setting I already mentioned is that you actually use this ACE protocol to distribute the keys. And then there are other ways where you can set up either using third parties or using certificate-based authentication, where you can, for other reasons, trust this party it's been issued a certificate from a valid party, so you could therefore authenticate. So, and there's a third protocol here, which is called ad hoc, which I will not talk about today, which is actually doing Diffie-Hellman key exchange, also based on these primitives, CBOR and COSI, and carried with co-op messages. So, and the final protocol I like to speak about is the protocol is going back to the problem statement that Martin was formulating. How do we make enrollment very simple for these things? And here is one very, very straightforward proposal that we have just started working on, which is saying that we already have things like enrollment using transport layer security. That's called EST. And now can we carry this over to application layer, where we now have the same type of protocols? We have a handshake protocol, which is this ad hoc, this Diffie-Hellman handshake. We have a communication security protocol, which is always co-op. And then just mapping the same type of enrollment protocol to application layer works very nicely. So I think I'll skip that part. I just put here, if someone is interested, to go back to the sources. This is work in progress. Some of this is finalized, and some are in late phases. But everything is work in progress, almost. So it's a large puzzle to handle. So as a summary, if we look back from the time when we started, many of the IoT security challenges that we faced 8 years ago are still relevant. It's still the basic security that's missing, and maybe the reason why this is missing is because it's not a huge cost for, the costs associated with adding security to devices is somehow not taken by these. The major cost, if someone is making a denial of service attack of DNS servers, is not taken by the company who is producing the CCTV cameras. So they don't really have the high incentives yet, but I think they should. And I think we agree. At least according to this analysis, this is what is still the thing that will also drive business in the future. That you have a sufficiently secure solution to not do things like overloading. These obvious attacks. So we are working on these new application layer security protocols, addressing end-to-end security, authentication, authorization, key establishment, key exchange, and certificate enrollment. So, any questions? Comments? Thank you.